All right, and then after they process that, I will post it online. So today we have 2 hours, so we're going to review 2 chapters. Chapters 22 and 24. And let's see where we're at. Okay. Yeah, and chapter 24 homework due today, or say tonight. So yeah, the solutions will be posted at midnight. So that to study. And then exam 3 is Wednesday. So after this, after Wednesday, we'll have 1 section left. There'll be 2 labs in that section, but yeah. Okay, so any questions before we get started? Okay, so let's look at chapter 22. We start with Faraday's law, which is one of the fundamental equations. I'll put that label, we're talking about magnetic flux. So if there's a magnetic flux through a surface, there will be an EMF around the boundary of that surface. And that minus sign is there, which for what we're doing with Faraday's law, we usually ignore. It's important because this actually shows a relation between electric fields and magnetic fields. So that minus sign is important. But usually what we're using it for, we have a, like say, a conducting loop. Let's actually do this. Say we have a conducting loop like this, and say there's a magnetic field coming out of the board. And then a short time later, say the magnetic field is 0. So we had a magnetic field coming out of the board. Say a second later, the magnetic field is gone. And so obviously the magnetic flux through this surface is changing. And so that will give rise to an EMF. And if this is a conducting loop, that will drive a current, called the induced current. So the question is, what direction would the induced current be? Clockwise or counterclockwise? So yeah, we're getting to the point where, you know, hopefully be pretty familiar with this by now. Don't want to take a shot at this one. Okay, so the flux is initially out of the board, but it goes to 0. So the change in flux, picture it's out of the board, but it's shrinking. So it's, you know, going, the change in flux is into the board. And so at Lenz's law, the induced current will create a flux out of the board that would be counterclockwise. So while the flux is changing, while it's decreasing, we would have a counterclockwise flux in the loop. Okay, so again, that is Lenz's law. Now, an important application of Faraday's law. Now, the reason for the most important application really is when we have a rotating coil. So say we have flux like this, we have this coil that can rotate, and we rotate it with an angular velocity omega. In this case, the flux is always changing. And so, like the flux, I should have written down what that is. So yeah, because theta is always changing. Theta is the angle between the magnetic field and the normal vector. And if it's rotating, theta is always changing. And so the flux is constantly changing. However, it's both increasing and decreasing. So the change in flux can be positive or negative. So the EMF is going to be positive or negative as well. And the EMF that we would get out of this can be described by a sine or cosine function. I mean, really, sine and cosine have the exact same shape. They're just shifted with respect to each other. You can use either one to describe this. And this is how most of our energy is delivered. This would give rise to an alternating current, because EMF can be positive or negative. So we also talk about alternating current in this section. So I'm going to look through the topics, and then we'll just do problems. I think we're just going to talk about alternating currents, really. And then we'll do problems until 9 o'clock. And then start chapter 24. So yeah, Faraday's law, Lenz's law, generators, and then alternating current and induction. Okay. So for the EMF, positive or negative, and so the current we would get out of this, and we plug into a power supply like this, is alternating current. Now, for a regular outlet, we would have maximum EMF of about 170 volts. So you know the outlet's 120 volts, but that's the RMS average value. The peak value is about 170 volts. And I think the frequency is 50 hertz. So like 50 cycles per second. The angular frequency omega would be 2 pi times the frequency. So be like 300 radians per second would be the angular frequency. So yeah, how the voltage and current, how the peak values and the RMS values are related, they always have that square root of 2. So the EMS voltage would be the peak value over the square root of 2, and the current that we get out of this would be the peak current over the square root of 2. Now, the power is going to fluctuate as well. But again, it's going through 50 cycles a second, so it's fluctuating very rapidly. You're not going to really see it going up and down, but it does. And so we can talk about the average power, where this is just a straight average, not an RMS value, because the power is always going to be like in one direction. So basically we just get 1/2. There's 2 ways we could write this. It's 1/2 the peak value. It's probably more useful to write it like this. And then if you just plug those values in, you can see that that's the peak value over 2. So 1/2 of the peak value. And then the last topic in this, we talk about inductance. So again, if we have a circuit, say we have a switch, battery, and a resistor. So, we know if we close the switch, we're going to get a current. That current will be going clockwise. And this clockwise current will create a flux into the board. And so there is a changing flux in this circuit. So by Faraday's law, there'd be a back EMF around the boundary. And actually calculating that would be extremely difficult, just because we would have to calculate the magnetic flux at any given moment, which would vary, around we have to calculate the flux through the entire loop. And that would be a difficult thing to calculate and then see how it's changing in time. Very difficult calculation. However, we could measure it. Basically, the EMF that we would get, we can say it's proportional to the rate that the current is changing. So if you have a rapid change of current, that'd be a rapid change in flux. And so that would give rise to a large EMF. Smaller change in current, smaller change in flux. And to make this an equation, we introduce a constant, which we call self-inductance. And that's because it's the current in the circuit that is causing this, this EMF in the first place. This would be a minus sign again. We're just looking at the magnitude here. So L is the self-inductance. It's measured in henries. And again, very difficult to calculate, except one case where we can calculate it. It's in the notes. That would be for a solenoid, but that's the only one that we can realistically calculate. Now, say we put another conducting loop nearby. If we flip the switch, we can actually see a current in that loop that's not connected to the power supply at all. Because these magnetic field lines also exist outside of the circuit. These currents create magnetic fields around them. And so there'd be, like in this case, there'd be a magnetic field out of the board due to the current here. Now this wire above, that would create a magnetic field into the board, but this one's closer. So overall, we would have a magnetic flux out of the board when this current is established. So let's say we open up the switch. Now, what direction will the induced current be in this ring beneath the circuit? Clockwise or counterclockwise? Okay, so no one wants to do Lenz's law. Okay, so while this current exists, there would be a flux out of the board. So if we open the switch, the current disappears, not instantly, but it'll disappear. That flux will disappear. So we had a flux out of the board, but it's going to go to zero. So the change in flux is into the board. So the induced current will create a flux out of the board. So that would be a counterclockwise current. So like after you open up the switch, this would be a counterclockwise current. It would be very quick and also very weak because the magnetic field here would be fairly weak. But yeah, So that, yeah, the direction, you find that from Lenz's law. Now, what kind of EMF are we getting in this loop? Well, this is mutual induction we're talking about. And again, calculating that would be extremely difficult. We'd have to look at the magnetic field in this region due to all these wires and then see how that changes in time. We're not going to do anything like that. But what we can say is that the EMF would be proportional to how quickly, so this would be the primary current that's driven by the power supply, and it's a change in the primary current that creates that secondary current. So we can say that the EMF in the secondary current is going to be proportional to the rate of change of the primary current. So for mutual induction, yeah, the EMF in the secondary coil is proportional to the rate of change of current of the primary coil. And if you want the direct, I didn't include the minus signs for either of these. Like if you want the direction of the induced current, use Lenz's law. So those are the topics for chapter 22 that we're going to go over. So is there anything in particular you wanted to look at, or oh yeah, sorry, there is one more thing. I should have left more room on here. Another example of mutual induction is the transformer. And but we'll do a problem with transformers, but I won't write it down until we get to it. All right. So any questions on chapter 2? We probably have time to just go over, a problem from each of these topics. So let's just do problems here. All right, so chapter 22. All right, so we'll start with let's see if there's something involving the right-hand rule. This might be interesting. So let me draw this picture. And we have this rectangular loop that's partially in the magnetic field. So let me read this problem. A long, narrow, rectangular loop of wire is moving towards the bottom of the page with a speed of 2 centimeters per second. The loop is leaving a region in which a 2.4 Tesla magnetic field exists. The magnetic field outside the region is 0. During a time of 2 seconds, what is the magnitude of the change in magnetic flux? So we want to know what is the change in flux over a 2-second interval. All right, so that wasn't in the written description, but let's call this the width. That is 8 centimeters. That was just in the picture. So it's 8 centimeters wide. They don't tell us the length, but we don't need that. Okay. So right now, this is all the information we were given. Let's call this here. Let's call that Y. Like the amount of this rectangle that is in the magnetic field. We'll call that Y. We don't know what that is, but it doesn't really matter. So right now we can say that the initial flux, that's going to be just the magnetic field times the area that's in the magnetic field. It's 0 outside, so we just ignore that part. So that would be B and times W times Y. So that's the initial flux. Now we can't actually go any farther with that because we don't know what Y actually is. So that's it for that. Now, 2 seconds later, it's moving 2 centimeters per second. So 2 seconds later, the whole thing moves down 4 centimeters. So this end, so basically Y is going to be reduced by 4 centimeters. So the final flux, we're going to have the magnetic field times W times Y minus 4 centimeters. So, any questions on that? Okay, so the change in flux, let's distribute that. We'd have the final flux, which would be BWY minus BW times 4 centimeters. That was the final flux. And then, change is final minus the initial. So we subtract the initial. We just cancel out that term there. That's why we weren't given how much was initially in the in that region. So the change in flux would be minus BW times 4 centimeters. So when we plug it in and get a number, we have 2.4 Teslas times W, which is 8 centimeters, and then times 4 centimeters. I don't even need fractions here, but they're there. So we have 2.4 times 32. So we have 76.8, or say 77 Tesla centimeters squared. Now, those aren't the base SI units. We could convert to meters squared, but why don't we just leave it like that? So that was a problem in the book. Now, why don't we expand the, first, any questions on finding the change in flux? All right, so let's expand this a little bit. Let's say the resistance in the wire, the wire has some resistance. Again, it would be throughout the entire wire, but just schematically, we can just put a resistor in there and say the rest of the wire has no resistance. Let's say that's 12 milliohms. So that's the resistance in the wire. And I want to know the EMF in the loop due to this changing flux. What is the induced current And what is the direction of the induced current? So there's a changing flux in this loop that will give rise to an EMF. We can calculate that. And if we know the resistance of the wire, we know the EMF is going to create a current. We can find the current using Ohm's law. And for the direction of the induced current, we will use Lenz's law. So let's start out by finding the EMF. Just the magnitude of the EMF. So there'd be the change in flux over time. So we'd have 77 Teslas centimeters squared over. So just delta phi over delta t. Now we're going to have to get volts out of this. So I want to convert to all the SI units. 1 meter is 100 centimeters. And we square the conversion factor because we have centimeters squared. Now, to get volts out of this, let's see. We have Teslas. I want to get rid of that. A Newton times a second is a Coulomb times a meter times a Tesla. And a Newton times a meter, so like a joule is equal to a Coulomb volt. A Newton times a meter is a Coulomb volt. Let's check. We have a Tesla, centimeters squared, meters squared, Newtons, seconds, coulombs, and volts. So hopefully everything will cancel out except for the volt at the end. Here we have a second, centimeters squared, Coulomb, meter, Tesla, Newton, and meters. So we are going to get volts out of this. Now let's get the number. Let's do 77 over 2. Let's see, that would be like 30, let's say 39. We'll round off to 30. I think actually 38 is probably better because we rounded up here. So let's say 38 volts, but 38 times 10 to the minus 4 volts. Or 3.8 millivolts would be the EMF. Okay, so while this thing is moving in this magnetic field, we'd have an EMF of 3.8 millivolts. Okay, kind of straightforward. We know the change in flux, all we do is divide by the time. The only challenging part would be getting the units to give us volts. So any questions on that? Okay. Now, what about the induced current? Kind of running out of room on the board. So we can just use Ohm's law. The current would be the EMF over the resistance. So we have 3.8 millivolts over 12 milliohms. And a volt over an ohm, the milli part just cancels out. A volt over an ohm is an amp. So 3.8 over 12, 4 over 12 is like 0.33. So let's just say 0.3 amps. So while this change is happening, while this is moving, we would have an induced current of about 0.3 amps. All right, and now the challenging question, what direction is this current going to be? We know there's going to be an induced current. So what direction? Do we want to try? Okay, so the flux is out of the board. But as we're pulling down this rectangle, the flux is decreasing because there's less region inside. So the change in flux is into the board. And so the EMF, the induced current, will be out of the board. So that'll be a counterclockwise current. That's what would be induced in this loop. Okay, so any questions on that problem? I'm gonna look at. I'm gonna find something involving like alternating currents. Okay, so let me see, alternating current kind of problem. Let's make something up. I didn't find anything really, nothing that would relate to the test here. Well, maybe this one. All right, this one would be the only one in the book that might be. I think the book actually introduces alternating current earlier than this chapter, which is kind of weird because you can't really understand it until we get to Faraday's law. This question is actually comparable to what we're doing here. So let's see, a generator uses a coil that has 100 turns. So 100 turns and a 0.5 Tesla magnetic field. The frequency is 60 hertz. And the EMF has an RMS value of 120 volts. So assume that each turn of the coil is a square. So that's not exactly, so it looks like that, except it has 100 loops. So loop around 100 times and then the wire would come out. Again, you probably wouldn't build a generator with a square cross section, but yeah, basically this isn't a magnetic field. You rotate this thing and with a frequency of 50 hertz. And yeah, we want, what the question is asking is determine the length of the wire. So just how long is this actual wire? So the flux in the generator, I didn't actually write down the relevant equation here. Pretty sure it's in the equation sheet. You're gonna write it like this. Let me write it this way. I'll write it like this. So theta is the angle between the magnetic field and the normal vector. And because this coil is rotating with an angular frequency omega, we can say that theta, the angle between the normal vector and the magnetic field, we can say that is equal to omega t. So like it's the angle is changing at that rate. So as long as we like start the clock at the right time, you can say theta equals omega t. And so here we have BA cosine theta. Well, theta is changing with time at this rate, so we can write it that way. Now the EMF in this case now again, I'm pretty sure this is in the equation sheet. Should probably check that. So yeah, for a generator, okay, so yeah, I have what's in the equation sheet is EMF equals Emax sine omega t. And then beneath that, we have Emax is NBA omega. So essentially, here we just have BA omega. I should put an N in front because there's N loops. So yeah, the flux, I forgot to put the N here because there's 100 loops. So yeah, we have the same thing. This is on the equation sheet, just in two pieces. Okay. So for a generator, that's the EMF. All right. And this would be the peak value of the voltage, because sine has a maximum value of 1. So this has to be the maximum value. So the RMS value would be the maximum value divided by the square root of 2. Now we have to do one more thing here. Omega is equal to 2 pi times the frequency. So like frequency is a number of cycles per second. Omega is the angular velocity. That would be in radians per second. And there's 2 pi radians in one cycle. So yeah, we're given the actual frequency. So let's replace omega with 2 pi f. And we can even simplify this a little bit. We can write 2 as the square root of 2 times the square root of 2. And area, I'm going to write as L squared. Because it's, we're told that the coil was a square. So it has sides of length L. And now I think we have everything we need. We want to solve for L. So we know ERMS, we know N, B, and F. We are out of room on the board, but I'm going to erase this and just solve for L squared. So let's see, we have square root of 2 pi N B F. So that will be L squared. And then it's a matter of plugging things in and getting the right units. So before I erase this over here, We have ERMS, and then let's see, square root of 2 pi NBF. Okay, so let's do this. So we've got 120 volts. N is 100. So let's do this. 100 times the square root of 2 will be about 141. Now B is 0.5 Tesla. I'm going to write it this way. So like 1 Tesla over 2. And then we have frequency, 60 hertz. That'd be cycles per second. So we're supposed to get meters squared out of this. Basically, what we have is volts times seconds over Tesla. And we want to convert these to more mechanical units. So a Coulomb meter Tesla is a Newton times a second. And a Coulomb times a volt. So a joule is equal to a joule is equal to a Coulomb volt. See what we're getting out of this now. So we have volts times seconds times Coulomb, meter, Tesla, newtons, and meters. On the bottom, we have Teslas, Newton, seconds, Coulomb, and volts. So we actually do get meters squared out of this. And yeah, let's look at the number then. We have 240 over 60, that would be 4. So 120 times 2 over 60. So 4 over 141 pi. So we're going to get a very small number here. Makes me wonder if I'm doing something wrong. Because if we're going to wrap it around 100 times, I would expect to have a significant amount of wire to do that. So I'm missing something. Yeah, that seems a bit weird. Well, why don't we go with it? Let's convert to centimeters squared. We'll get a bigger number at least. Okay. So we have 4 times 10 to the 4th over 141 pi centimeters squared. So it's what I'm going to do, let's do 141 pi first. 443. So let's see. So I'm getting about 90.3 and then taking the square root. Yeah, I'm getting L is 9.5 centimeters. Yeah, very, very skeptical of that number because it's, it's not much wire to work with. You're going to wrap it around 100 times. It's an odd number in the book. I'm sure it's wrong, but I'm just going to look it up anyways. It just seems way off. So this is chapter 2245. Yeah, the answer is 38 meters, not 9.5 centimeters. So trying to figure out what I did very wrong here. The numbers are right. Yeah, that number is just way too small though. So let me this is the calculation that we did. So let's see. I put these in here right. Yeah, we've got 100 on the bottom. All right, so I'm going to check this part. So yeah, the going back to the beginning, the maximum EMF was N BA omega. That's in the equation sheet. So the RMS value would be this over the square root of 2. A is equal to L squared. And omega is 2 pi times the frequency. So let me just check. So yeah, we have omega NBA. Yeah, and then we did this. Yeah, it looks like this formula is right. Put in the numbers right. Not sure what actually went wrong here, but that answer is completely ridiculous. Can anyone see anything that's not making sense here? Yeah, that 100 turns. Oh wait. Okay, I think I know what I did wrong. I said L is the length of one side of the, in the picture. So I said area is equal to L squared. That's obviously not the length of the wire. That would be the just one little segment here. So I was just calculating the wrong L. Okay. So L, I had 9.5 centimeters. So if we multiply this by 4, let's get like going all the way around the thing. 9.5 times 4 would be 38. So just going around this square once, that would be 38 centimeters. And so let's say capital L is the length of the entire wire, but we have 100 loops. So going around once is 38 centimeters. Yeah, if you multiply by 100, you would get 38 meters. So that's a case of just not really paying attention to what I was actually calculating, but that makes much more sense. So this number was right, just not what the question was actually asking for. Okay. So any questions on that one? All right. Let's look at a transformer question. But I didn't write that down. So, you know, what's next is we have EMF, like the due to mutual or self-induction, and a transformer is an example of mutual induction. So let's do this. We have a transformer, which we can represent schematically. You know, we have these two coils. We have a primary current here and a secondary current here. This marker is kind of fading on us. All right, so we have just a different number of coils in the primary and secondary. And the basic transformer equation is that EMF in the primary coil, or actually I'm going to write it this way. The turns ratio, so like the number of turns in the primary coil divided by the number of turns in the secondary coil, that's equal to the ratio of the EMF in the primary over the EMF in the secondary. And again, this is like an ideal transformer. And because the power is constant, we're assuming that there's no energy loss going through the transformer. Then we have this inverse relation here in the actual currents, because the power is the current times the voltage. So if we just like cross multiply, you know, EMF in the primary times the current in the primary, that'd be the EMF in the secondary times the current in the secondary. Basically, that last equation here is just saying that there's no power lost. Now, of course, there will be power lost. Usually, for actual transformers, I think they can get efficiencies of, you know, significantly over 90%. So for what we're doing, this is fine to just leave it as that. Okay. Now, let's see if I can just find something we haven't done here. Here's a simple one. A step down transformer. So a step down, that means it reduces the voltage. So a step down transformer with a turns ratio of 1:8 is used with an electric train to reduce the voltage from the wall receptacle to a value needed to operate the train. When the train is running, the current in the secondary coil is 1.6 amps. And what is the current in the primary coil? Now, it's a step down transformer. So you're plugging this into a wall outlet, like 120 volts RMS. We're going to get 1/8 of that on the other side. So we just have to write the ratio properly. So let's see. Yeah, so that would be a step down transformer. Writing the ratios 1/8. That way you can see like that's equal to the EMF in the primary over the EMF in the secondary. So the EMF in the primary would be 1/8 the EMF in the secondary coil. So the voltage is reduced. So we want to find the current in the primary coil. Let's just flip this upside down. We can say that the current in the primary coil over the current in the secondary coil is equal to the number of loops in the secondary divided by the number of loops in the primary. So if we solve for the primary current, we have the secondary current times NS over NP, which is 8. So we have 8 times the current in the primary coil. Wait, let me see if this is making any sense. Okay, so yeah, I'm sorry. I think I wrote this fraction wrong. It's a step down transformer. Let's come back to this part here. Yeah, if we write it this way, I mean the EMF in the primary coil would be 1/8, just kind of reading it backwards, times the EMF in the secondary coil. Sorry, that would have been a step up transformer. I was thinking about that backwards. Yeah, the EMF for a step down transformer, the primary should be at a higher voltage than the secondary. So I should have written this as 8/1. And now we have the EMF in the secondary coil would be 1/8 what's in the primary coil. So sorry about that. But yeah, this one makes sense. The EMF in the secondary coil is 1/8 what's in the primary coil. So this is 120 volts here. And in the secondary, we'd have 1/8 that. So it'd be like 13 or something. Let's see, 120 divided by 8. 12 over 8 is 4/3. So yeah, I think that's 15. Yeah, that one makes sense. Okay, so this would be 15 volts here. So that's a step down transformer. We drop the voltage, but in order to keep the power consistent, that would be in a greater current. So the current in the primary coil would be 1/8 of what is in the secondary coil. So this would be 0.2 amps. So you could check like 0.2 times 120, the power delivered to the primary would be 60 watts. And over here, 15 times 1.6. Wait a minute. Sorry, it is definitely a Monday. Nothing is working out. Go back to yeah, that's right. 15 volts. 1.6 divided by 8 would be 0.2. Yeah, 120 times 0.2 My inner calculator is very off today. Didn't get much sleep last night. But yeah, now it's all working out if I can do arithmetic properly. Yeah, 120 times 0.2, that's 24 watts. 15 times 1.6 is also 24 watts. So the power is an ideal transformer when nothing is lost. No energy is lost. The power of the primary and secondary coils are equal. So the step-down transformer, we reduce the voltage by a factor of 8, but we multiply the current by that same factor of 8. Okay, so kind of a basic transformer problem, and that's an example of mutual induction. Okay, so any questions on chapter 22? Okay, so move on to 24. Okay, I'm going to stop recording and then start again so I can get 2 videos and just have one of each. So do that real quick.